So the following lecture is given by Sibylle Hess. So she is an assistant professor of data mining at TU Eindhoven in Netherlands. She completed her PhD in 2019 with Katarina Morik's lab at TU Dortmund as an employee of the Collaborative Research Center SFB 876. She has been a PC member of various top conferences such as NeurIPS, ICML, KDD, ICLR, ECML, PKDD, and others. And also she has received a top reviewer award at ICML 2020. So today she will talk about metrics, factorizations. So Sibylle, now the stage is yours. Yeah.
Okay, thanks a lot for the nice introduction. So the microphone doesn't work at the moment. If you can't hear me, just raise your hand or like give me a sign like this or so, then I now have to pump up my volume. So what I want to do today is to give an overview about the jungle of matrix factorizations. And we have quite the journey from SVD, like singular value decomposition, to deep learning, and see how everything is actually connected. But first, we're going to start a bit fluffy. So just to introduce myself, I come actually from Dortmund, but I live now in Eindhoven. It's just 150 kilometers to the west. So it's not so far away. I did my PhD here in this collaborative research center in the project C1, which was more biologically inspired and which had to deal with high dimensionality in particular. I defended my PhD then in June 2019. So here you see my supervisor, Katharina, and also Arno Sivis and Erich Schubert. And yeah, I also married in 2019. Actually, my coworker, I met him here. He was a postdoc and I was a PhD student. And now we are actually both assistant professors at the TU Eindhoven. So this is the data mining group. Our full professor is Mykola Pieczenitsky. And this is like me and my hubby and other people. And you might know also Joaquin van Stroren. He's quite famous in the AutoML community. So this is the data mining group, and then we have also PhD students, but we also have a UAI group. So in total, we have quite a big team working on AI. And I've worked on robust clustering, determination of the number of clusters automatically, optimization subject to binary constraints, and deep learning as kernel k-means, of which we will see some of this today. Now, the outline is a bit that I wanted to start with SVD and PCA, then a bit about non-negative matrix factorization, then we have a short break and you can ask some questions. And then we go over to clustering and non-convex clustering and biclustering, and then to deep learning and the connection to clustering actually. Okay, so matrix factorization is a jungle. I'm referring here to one of the sites I've used as a PhD student quite often. It just summarizes quite nicely how constraints in your matrix factorization objective induce novel learning tasks and how these learning tasks are correlated. And yeah, matrix factorization together with constraints yields a lot of known tasks such as non-NMF, k-means, or probabilistic latent semantic indexing, independent component analysis. All of this is some kind of matrix factorization. And if you know one, then you know them all a bit. So it's quite interesting to see what are the core principles here. Now, generally, matrix factorization has the goal to approximate a given data matrix D. So here the data matrix D has the rows are the data points and the columns are the features. And then we want to approximate the data matrix D with a low rank product. So that means that you see here, yeah, the rank is here now, for example, 3. So you see here that we have Y is like dimensionality of the data points times 3, and X transposed is here actually the number of features times 3. Okay, why would we do that? Now, the general thing is that matrix factorization compresses. So if you approximate your data matrix with this low rank product, then you need to store far fewer values. So for example, just take like D as a 100 times 200 dimensional matrix, which is quite small actually. If you store D, then you have to store 100 times 200 values, which are 20,000 values. If you approximate D with the rank 3 product, then you just have to store 900 values. So the number of values you need to store actually goes down a lot. And this is not, this is just like one idea, but like side effects are also that you can actually mine results of your data from the low rank product, basically. And to do so, it's quite interesting to see the low rank product as a basis coefficient derivation. So what the matrix factorization does is basically finding a new basis in which your data can be described succinctly. So basically it finds basis vectors, which are actually represented here in X. So those are basis vectors, and Y actually then represents the now low dimensional coordinates. So for example, if you want to approximate here the first row of A, then what you do is you multiply the first row of Y times X transposed, right? So in math, it looks then here like this. Or we can just like visualize it a bit. So here we have one row of A, and here we have the row of Y, and then we multiply it with X transpose. And what happens basically is that Y denotes coefficients for your basis vector. So every color here indicates one basis vector in which your data is now represented. So X gives you a new basis for your data. So it can also be interpreted as patterns that occur frequently in your data. And Y gives you then a new low dimensional coordinate description. Okay, let's have a look at some examples. You probably know SVD, singular value decomposition, and PCA. If not, let me explain it a bit. So singular value decomposition usually has this tri-factorization form. So on the left, you have the left singular vectors. In the middle, you have the singular values. They are ordered by magnitude. So the largest singular value is here the first one, and then the second one follows, and so on. And then you have the right singular vectors. And this optimization scheme of SVD actually is the solution to this optimization objective here, which is to minimize the approximation error of my data matrix D minus the low rank product in the Frobenius norm. So you cannot have a lower approximation error than by using truncated SVD. And we know then that Y X transpose actually has to have this form. So we multiply these truncated three matrices. And the full SVD is actually describing my data matrix entirely. Do you know SVD? Who knows SVD actually from before? Okay, nice. So let us have a look at an example. Now here I've used the Olivetti face data set, which is just pictures from faces of people from various angles. And what I wanted to do here is to have a low dimensional representation of my data. So here you see the data points, which are basically the images. And every image is at the coordinate that I get now by my matrix Y. And the coordinates here, so basically the axis or the interpretation of the axis is given by my basis vectors, which is here like the first singular vector, which looks here a bit like actually like the average face. And the second basis vector would then here be this picture. And then you see that, for example, from the left to the right, your pictures become more liked, right? So you see here are the pictures a bit more darker, and here they are a bit more liked. So that means the amount to which this basis vector is used determines the likeness of the pictures. And here, this picture basically describes where does the likening come from. So here, in this coordinate, the likening comes actually from the left. And then you see also that those people who are here on top actually have their face more illuminated from the left, and those below have their face more illuminated from the right. So this is here an explanation of like the latent space that is actually induced by SVD and how SVD can be used as a dimensionality reduction technique. Now, quite related to this is principal component analysis. Do you know principal component analysis? Nice. Very good. So yeah, the idea is to find the directions of maximum variance in your data. So the typical example is that you have here this point cloud. And then you want to find the directions that when you project your data onto these directions, you get the maximum spread, so the maximum variance. So the direction of maximum variance here is denoted by my first basis vector x1. So if I project everything on x1, then actually you see that the spread should be like the largest, right? If I project then everything on x2, so this is actually the direction of lowest variance, then I see that it probably will not spread so much, right? It will be just like this. And then what PCA does is basically rotate your data such that now these directions of maximum variance align with the coordinates of your coordinate system. So PCA finds the direction of maximum variance, and yeah, in math you say basically that you want to find a left orthogonal matrix. So the basis vectors have to be orthogonal to each other, and the first basis vector actually solves this objective, which is to maximize the variance if I project my data on basis vector x1. So multiplication actually of your data matrix with the norm 1 vector computes a projection geographically. This is always the case. And the solution to principal component analysis is also given by SVD. So if you center your data matrix, so you just subtract the mean from all the rows, and then you apply SVD on your centered data matrix, then you get actually the solution to PCA. So here we have then X is equal to VK, so the truncated right singular values. Those are the principal components, and Y is here the matrix UK times the singular values, and the singular values actually also correspond to the variance that is captured in each direction. So interesting, principal component analysis is basically SVD on centered data matrix. But now the SVD has this nice interpretation of maximum variance direction. I find this quite neat. So let's have a look at the same example again. So here the first coordinate now changes a bit. It doesn't really look anymore like the mean phase, because actually the mean phase is now subtracted from my data before I use SVD. So now this basically just indicates a bit more like what is the variance, you know? So here, you could say that this is showing more like an illuminated face, which is like really photographed from the front. But the rest is quite similar. And the thing is that truncated SVD is also the solution of a linear autoencoder. So autoencoders, you have your input here. So you put in data point J, and then you find some weights such that if you multiply with them, then you are here in the middle in this compressed space, basically. And then from this compression, you want to decompress again to an image or to an input, an output that is similar to your input again, right? So mathematically, you want to minimize for every data point here the distance of your input dj to the projection of dj onto the weights of x, and then the multiplication of x tilde, which is basically the decompression. And yeah, this linear autoencoder objective actually has a solution, the right singular value. So basically x is here returning again this new basis, which is given by SVD. And this also introduces some interesting new research directions, right? Because when we know what actually linear autoencoders do, can we now say more about what effect, for example, the addition of certain nonlinear activation functions has, and so on, to get a bit of an insight into what is happening when we actually compute autoencoders. So, but this is only for the linear case. So how can we actually model nonlinear relationships? So the idea here is to use the kernel trick. Of course, in autoencoders, you have this other idea such that you actually use this combination of multiplication with the matrix and then nonlinear activation functions and so on. And yeah, so let's go through just the idea of kernel PCA. So here, for example, you have the two moons data set. So they are non-linearly separable. That means that if you project this onto SVD, then you would probably intermingle the data points. So for example, if you just project on the first principal components, I would say that the maximum variance direction is actually here aligned with the axis. But then if you project everything onto the x-axis, then you will see that the points from the two clusters or the two classes would be intermingled, and you don't want that, right? You want to have a low dimensional representation, which makes everything look neat. So linearly separable is neat. And the idea of the kernel is that you actually compute the feature transformation to a probably higher dimensional space in which actually everything is neat and linearly separable. But we don't want to compute the feature transformation phi, so we just want to have our kernel matrix and then work on that. And if you think about it, so you just assume we have phi, which in practice we do not. Then the PCA coordinates of phi from C are actually given by the matrix Y, which indicates here this left part of the SVD. Now, if you multiply phi from psi times phi from C transpose, so basically here this kernel thing, then you will see that you have in the middle V transpose times V. So this cancels each other out because V has to be orthonormal. And then you can also just compute the eigendecomposition actually of your kernel and then set the coordinates accordingly to this formula. So basically in kernel PCA, you lose this interpretation of the variance. So because you don't have these directions anymore, you don't know what your transformed feature space looks like. But you can still get the new coordinates. And if we do this here for the RBF kernel, so in the RBF kernel, basically everything which is close is also represented to be as close in the kernel. But everything which is a bit further away will be pushed even further away or represented to be further away than it actually is. And then if we use the RBF kernel and then we apply kernel PCA to it, then we see that here we have now a representation which would be actually approximately linearly separable. Okay, so if we look at our faces, what do we get then? Now, I would say that you have a bit of a more clustering feeling here now, because the local similarity of pictures are actually important here and are also still reflected. So for example, all the beard dudes are here. Here we have people with glasses. This guy looks menacing, they're there. Like you see that it's more related to like local similarities. It's not so very straightforward anymore, like, okay, this side is illuminated and the other one not, although you could also say that in this direction, like the illumination takes off. Okay, so let's have a look at some research directions. So as I said, what I find interesting is to analyze autoencoders from the perspective of matrix factorization, because there we can say more about these black box models. And there have been some first papers actually in doing so. Then also truncated SVD is polynomially solvable. It's super fast, and there exist a lot of even faster methods for having special situations, like, for example, if you have sparse data or something like that. But still, this is a topic of research, more from the mathematical side, I would say. And also, what is generally interesting is to transfer now these best practices from matrix factorization and deep learning. So for example, you can analyze in matrix factorization the effect of dropout. And this again, you can then apply to the deep learning methods. Okay, any questions so far? No. Okay. Now, we have seen that rated SVD, so this was the best we can do in the Frobenius norm. But we have also seen that SVD has a bit of an interpretation problem. So interpreting these real valued factor matrices is generally not easy. And this is why we want to add now some non-negative constraints. And here, basically what we do is, again, we want to find a low rank product which approximates my data in the Frobenius norm, but now I want to have only non-negative matrices. Now, the non-negative SVD, unfortunately, end presentation. So for example, if you look at the new basis vectors for truncated SVD, so here we have a higher rank, it's a rank of 9 or something. No, I don't know, actually, I didn't check. A higher rank, you see it. And then you see that these basis vectors have like something people often refer to as holistic faces. So they're like whole faces, you know, they look a bit transparent and sometimes creepy, but they're whole faces, and it's a bit difficult to say now what actually it means that, for example, the coordinate for this basis vector is high, right? So you can say, okay, then it's more similar to this man. What is this? He has like very light eyebrows. I don't understand. Now, if you use NMF, then you see that NMF highlights here parts of the face. So for example, here you have it's a bit wider. And so this is nice, but we have this optimization problem. So this introduces the whole area of, you know, like non-convex optimization. And in general, now yeah, let's have a look at actually the properties of this objective. So if we want to minimize here this approximation error of the data matrix to the low rank product, then this is actually non-convex in its arguments. But if we fix one of the matrices and only optimize subject to the other, then it becomes convex. Actually, if you fix here, for example, y, and you optimize only over x, then this is also equal, or the objective to multi-target regression problem. So D is then giving you your targets, like multiple targets, and y is the design matrix, and x basically is this beta vector. And you might remember from regression that actually regression is a convex objective, so here it's basically the same. Now, if you have this situation that it's non-convex in both variables, but convex in one, then a logical thing would be to do alternating minimization. So we always fix one of the matrices and just optimize subject to the other, and then we fix the other matrix and optimize subject to the other, and so on until we arrive at a minimum. But to make this fast, we actually need to solve here this optimum analytically. Because if we want to apply optimization techniques to find this optimum in every step, then we have optimization within optimization, which takes forever. So the thing is, to make this efficient, actually, we would need to know the minimum, which we don't. Now, most popular non-negative matrix factorizations are lazy versions of alternating minimizations. So that means that we don't optimize the whole way down, but we just take a gradient step, basically. And one thing that is quite popular is to use multiplicative updates. So then you fix here in the first step y, and then you update x by a multiplicative rule, and then you fix x and update y according to a multiplicative rule. And they have basically the property that they are a gradient descent with a small enough step size such that the non-negative constraints are not violated. Now, the positive aspects are that the iterates stay non-negative during the optimization, which is quite nice. And other constraints are also usually easy to integrate. The thing is, yeah, the main drawback is that it has a really slow convergence. This is because the step size is always so small. And also once an element is 0, it always stays 0 because I just multiply here. So if I multiply with 0, then I always stay 0, right? So yeah, this we could maybe do better. And the way to do better is with proximal alternating minimization. So here we put basically our constraints in the functions phi. So for example, for non-negative constraints, we could say phi returns infinity if one of the values is negative, and otherwise it returns 0. And then the proximal updates are defined such that first we have here a gradient step subject to x. So we fix y and we update x. And then we prox this result such that it also minimizes phi. So this is here the proximal operator. And you can see that it's actually an optimization problem itself. So this again should be solved analytically. Phi shouldn't be too complicated. And what it does, it basically gives your solution that you have here. So solution X, it gives solution X a bit of a nudge such that it also minimizes the constraints. Now for non-negative matrix factorization, this looks then as follows. So we have here our gradient step, and then we just prox it by projecting onto the non-negative realm. And the step size is also given as is denoted here. And then we have a guaranteed convergence to a stationary point. There is a rich theory, there are inertial methods, there are stochastic gradient descent methods. There's everything you like in optimization theory available. And we also have no hyperparameters except for the rank. The contra is that the feasibility of additional constraints depends on the availability of the prox operator. So maybe you have to show it yourself. For many of the popular constraints, you can find a prox operator. And some research directions here would be actually what I find interesting is to analyze now these non-negative constraints, which are also rediscovered in deep learning, and to see if also in deep learning we see then this building block type of interpretation of the weights, which we know from non-negative matrix factorization. In fact, I think this would be quite desirable if we could find a latent space in the deep network, which basically reflects us or gives us the building blocks which compose the images or the classification of the image or explain how the network actually composes its representations. Then there is also a lot of theory about analyzing the effect of the loss function. So for example, if you minimize the Kullback-Leigler divergence, then you get a more probabilistic interpretation of your matrix factorization. So there's also a whole area of like analyzing the loss effect on the interpretation of your model. Okay, and now when we add binary constraints, then we actually arrive at clustering. So you probably all know k-means, so I hope this is a bit of a recap just. If not, that's also fine. And the k-means clustering model is as follows. So you have this notion of clusters which say that points within one cluster should be similar. So if I have a cluster, then all the points within it should be similar, and points from distinct clusters should be dissimilar. And then the mathematical objective is here this within cluster scatter, which you probably all know. So what it does is basically sum here over all the clusters. And then you compute here the average distance between 2 points in your cluster. So you want to minimize the average distance of points within your cluster. And these clusters actually create a partition of your space. So every point belongs to exactly one cluster. Those are the assumptions of k-means. And k-means is also actually matrix factorization. We just have here a small tweak to our general objective. And that is that Y now has to be a binary matrix, which actually indicates a partition. So I have ordered now, or just imagine that the rows are ordered such that consecutive rows belong to the same cluster. Then you get an optimization scheme like here. So for example, the first point here belongs to the first cluster because there we have the 1. And this point here would belong to the second cluster, and this point would here belong to the third cluster. And our basis vectors are becoming now the centroids, actually. So what you want to do basically is to approximate your data with its assigned centroid. This is the objective of k-means, or one of the objectives of k-means. And the set 1 to the power of m times k contains all binary matrices which indicate a partition of m points into k sets. So that means that y has to be binary and that the sum of each row of y has to be 1. So there's exactly one here in every row, which indicates the cluster the point is assigned to. So we do not gain, as optimizationally speaking, this is quite difficult because binary constraints are generally hard to handle. So how do we optimize the challenging combinatorial problem of k-means now? Now, in this case, we are extremely lucky because we can actually apply alternating minimization. And this is what you probably know as the k-means algorithm. So the first step is you initialize your cluster centroids, and then you compute the cluster assignment such that every point is assigned to the cluster with the closest centroid, right? Now this actually solves this objective of k-means, the matrix factorization objective, if we fix our basis vectors x and just optimize subject to y our cluster assignment matrices. And then in the next step, we update the centroids. And this again solves here the objective where we fix now y and optimize for our basis vectors, which are the centroids in this case. And then we go on and go on and go on until we converge. And this is the k-means algorithm. And we have an alternating minimization scheme for it, which is quite neat. Now, a bit of the drawback is that the exclusivity assumption is needed to make this optimization scheme possible, because when you say every point is assigned to exactly one cluster, it's quite easy to say which cluster is the best, which is the one with the closest centroid. But if you allow for overlap, for example, then it's a bit difficult to say, oh, does this point now belong to both clusters or not? Like, how close do the centroids have to be such that a point belongs to both clusters? Or like, how far away do they have to be? Like, how do I do this? Nobody knows. So the pro of this optimization scheme is that it has actually a very fast convergence, because in every step we minimize exactly. So we go down, 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 down. And there are no hyperparameters except for the rank. And yeah, cons are that it's quite sensitive to initialization. And I think this is actually due to the fact that we go very deep in each iteration. So for example, if you use gradient descent with this very small step size, you have a similar effect, right? So you start somewhere and then you go really down, right? So here we also, when we start, you know, we always minimize as much as we can. So in the end, you do not explore the space so much as you would, for example, if you use gradient descent with a bigger step size. And yeah, it's only applicable to partitioning clusters, so only if we really assume that every point belongs to exactly one cluster. But the good thing is now that we have alternating minimization, we can milk it. So we can cluster now basically everything with it. And the next thing would be to also derive non-convex clusters. So again, we apply the kernel trick to actually arrive at kernel k-means to get non-convex clusters. The clock is correct, right? We have just shortly past half. Okay, nice. Okay, so in non-convex clustering, let's have a look at the equivalent k-means objectives, because there's just not one. You know, we had the minimum cluster scatter, then we had this matrix factorization objective here. But actually, if you use the definition of the Frobenius norm over the trace multiplication, then you also get other objectives. And those are here those which maximize the trace. And these are interesting for kernel k-means because here we get now this matrix here, D times D transposed. So in this matrix, you can reflect similarities of data points, which are denoted by the inner product. So for example, you can see now clustering as a bit of a graph clustering thing. So if we plot here, for example, these two circles, and then every point is plotted as at its coordinate. And then I have here edges, which are as big as the similarity is indicated by this matrix here. So for example, I multiply this point in the inner product with this point, and then the result gives me the strength of that edge. And then you see that it does not really separate, like you do not see a separating way of these edges, except for maybe cutting this in half here, something like that, right? Because here the edges have like low connectivity. So here we have not such a dense connectivity, so probably we would cut here in half, but then we do not get a good clustering. Now, if we write this trace maximization thing out, then actually what it does is we sum over all the clusters again, and here we compute the similarity of points which in cluster C, where the similarity is given by this matrix here. So we basically compute the sum of all the edges which are here in cluster C indicated. So again, we have this notion of like points within a cluster should be similar. But what we can do now, instead of having D times D transposed, we can now apply a feature transformation again, and then apply just K here, right? So instead of D times D transposed, we can also say we have first a feature transformation, and then we call this here K. Now, what we do for kernel k-means is basically we go backwards. So what was here now D times D transposed, we denote this now at K as K. And what was before D, we denote here by H, and H is derived by a symmetric factorization of K. So for example, if you compare this here, so first we had here D, now we have H. So we go just the other way around. And the thing is that with K, we can again model only local similarities. So for example, if I apply here the RBF kernel to this data set, then you see that the outer circle is quite nicely connected and the inner circle is quite nicely connected. So this would mean for my clustering that if I want to have points similar to each other within my cluster, that I would now cluster the outer ring and the inner ring, right? So you see already in the similarity representation the clustering. Now, kernel k-means has an interpretation of a graph clustering method where K is the weighted adjacency matrix of the graph. But besides maximizing the similarity within clusters, also another objective makes sense, and this is the minimum cut objective. Now, the minimum cut objective basically says that if I have my similarity matrix here, now W, which you can basically see as the adjacency matrix of your graph, that you want to find clusters which minimize the cut. And the cut means that you take all the points which in cluster C, and you sum up all the similarities to the points which are not in cluster C. So we have here cluster C, we multiply it with the edge weights, and then we multiply here with those which are not in cluster C. So basically here you would like snip along the edges, like around your circles, and this would then also minimize your objective, right? Because here we have very, very low edge rates. Now this minimum cut introduces actually graph Laplacians. If you don't know it, it's not super important. But if you know graph Laplacians, I think that's a nice way to also like have a bit of an interpretation about it. Because if you compute here this term, so this cut term, then actually what it also, you can also state it as you compute here the similarity of this matrix, which is now the graph Laplacian. And then minimum cut is actually equivalent to kernel k-means. So kernel k-means has this objective, and this is equivalent to minimum cut when you use as kernel matrix this matrix where L is the graph Laplacian. And then depending on the graph Laplacian, you get also different results. So for example, the difference Laplacian is the one which gives you basically the connection from similarity clustering and minimum cut clustering. Then in practice, usually the symmetric normalized Laplacian is used because it's just more robust to noise. But you can also use the random walk Laplacian, which again gives you a new interpretation of your clusters, because if you use this Laplacian, then you can see clusters as an area in which you would stay. So if you start a random walk and you go to a next node with a probability that is relative to the edge rate, then in a cluster, you would always go to the points which are similar to each other, right? So you would likely stay in a cluster if you start in a cluster. And this is yet another definition of clusterings, which might be useful. Now you might have heard of spectral clustering. Does anybody know spectral clustering? Okay, no, it gets thin. Yeah, so basically it's the clustering method for non-convex things, which is more geometrically as an interpretation and not like probabilistic or so. And it's also, it's quite common actually. And spectral clustering is typically presented like this. So basically we have our data set and the number of clusters. And then we choose a similarity representation W. So for example, it could be RBF kernel, something like that. So something which is preserving local similarities. And then you compute the truncated eigendecomposition of the relaxed minimum cut objective. So actually we take here away these constraints that we have to have here clustering indicator matrices or binary matrices. And instead we just say that Z has to be left orthogonal. And then we get actually a solution. Yeah, the solution to this objective is again given by truncated eigendecomposition. And then this solution is relaxed, is binarized by applying k-means on U. Now the weird step here is why k-means? Like, why would I not just threshold my matrix Z to binary values, right? Because what I did in the end is just like compute the solution to the relaxed objective. And now I just need to put my relaxed objective into hard binary cluster assignment. So how do I do that? Like, why should I not just threshold it? So like at 0.5, everything which is over 0.5 gets a 1. But instead k-means is used, which just seems a bit weird, right? So the thing is also, it works quite well, but if you crank up the noise, then like you as a human, you still see that there are two circles, but the method doesn't really. So it just like tries to separate here in half, and it doesn't really make sense, and we don't want that, right? So, okay, we have here some weird aspects. And in this narrative, k-means is a discretization method, which happens to just work well in practice. Like we use it because it works well. But actually the application of k-means is well justified. So again, if we use this kernel k-means interpretation of minimum cut clustering, then we can compute a symmetric decomposition, which basically allows us again to go backwards. So we had this objective here, which is equivalent to minimum cut, where Z has to be defined by a binary matrix Y. And then we can put in here our symmetric decomposition. And then we see that this objective, so if you go a few slides back, you see that this objective is actually exactly equivalent to k-means on H, on my factor matrix H. So actually minimum cut is theoretically equivalent to k-means on H. But in practice, this somehow doesn't work. So if you see here, for example, this two moons example, and then we have here the objective, which is to maximize. And then you see that here, if we have this very non-OK clustering, that the objective is 2.039. But if we consider the perfect clustering, then the objective is just a tiny bit higher. But the difference between the two is like really big. And yeah, the hypothesis is that this exact factorization just spans a space which has the dimensionality of your data points. So this is a very high dimensional space in which k-means, a method which is working well in practice, but it's not guaranteed to find the global minimum. So k-means has to search in this very high dimensional space for clusters, and it just fails, you know? So what has to be done is actually to find some specific decompositions here, such that k-means has an easier job. And this I would propose as also a research direction. So actually we could show that robustness of spectral clustering can be improved when we apply k-means on specific low-rank decompositions, but I think we could do there even more. And in particular, in combination with the research direction to learn a suitable graph representation also automatically. So I'm thinking, for example, if you have, instead of these symmetric decompositions, you could also use an autoencoder, right? Because this also like compresses and decompresses your data, and you can apply k-means then on the latent space in the middle, basically. And the good thing would be to actually learn then the suitable graph representation of the similarity, the feature representation automatically. The thing is just, it's not as trivial as you might think. Here we arrive basically at deep clustering, where you want to learn the feature transformation that gives you a good clustering as well. And the ultimate goal, like which should be clear, is that we want to simultaneously optimize our feature transformation and the clustering such that both match. But this is still a very young area of research. So if you want to get into this, I would recommend here this paper. Okay. And now we discuss high dimensionalities, but I think we have first a short break of 10 minutes, just get something to drink. You can also ask me questions or go to the toilet. So we see us back at 5 minutes before 12. Should I stop this here?
Back up. You start? Yeah. Oh, you did already?
Okay. Back. So what we do now, we go now into the high dimensionalities where we have a problem with clustering, because in high dimensionalities, things are usually not similar to each other anymore. So we have here now the topic of biclustering. And the motivation for biclustering is, for example, movie recommendations. So if you, for example, imagine you have a database of users, which are the rows, and the movies, which are the columns. And then what you want to do is you want to find clusters of users such that you can say, hey, you belong into that cluster. The people in your cluster like these and these movies, you should watch these movies. Now, the problem is that the space of the whole movie space, basically all the movies we have, is just super big. So you will probably not find one single person which has a really similar taste in the space of all movies. Maybe your friend has like a similar taste like you in when it comes to horror movies or something like that, but usually you don't have a big overlap of on the space of all movies. And the idea of biclustering is basically to cluster the movies and the users together such that you can say these users are similar to each other with respect to only these movies. So for example, only with respect to horror movies. And what you get then are these tri-factorizations now, so a bit like SVD, but now again with these binary constraints. So what we have now is to minimize the data matrix approximation by y times c times x transposed. And y and x are now binary partitioning matrices. So y indicates the clusters of users and x indicates the clusters of movies. And C could be then, for example, interpreted as like the rating that people in this user cluster, for example, give to this movie cluster. So then that would be this area here. And then you can also make different assumptions. Like, for example, we do not consider arbitrary combinations of users and movie clusters, but we only have a one-on-one relationship. So for every user cluster, there's exactly one movie cluster in which we can denote the rating. And if you have binary data, then usually you don't need this core matrix, right? Then you might want to have a binary factorization because it's just interpretable. It stays in the realm of binary values. And then we have an objective which looks basically like this. So the core matrix is not here. And then we have y and x. Now, for all these cluster models, alternating minimization is possible due to the exclusivity assumption. So what people did is like, hey, I have here this biclustering model. I just milk my alternating minimization scheme known from k-means and apply this to 3 matrices. It doesn't change much. But especially for biclustering applications, if you think about it, the exclusivity assumption is inapt. So one movie does not necessarily belong to just one cluster, right? A movie can be a horror movie, but also starring one actor, which some people like, for example. So it can belong to multiple clusters. And what we want is a more free like modeling of clustering. So for example, we want to model overlap. So here we have, for example, overlap of user clusters. Here we have overlap of movie clusters. And here we have also some outliers. So these users cannot confidently assign to any of the clusters. And likewise, if we want to do this with binary values, then we arrive at Boolean matrix factorization, because in Boolean algebra, 1 + 1 is actually 1. And with this algebra, you do not penalize overlap between clusters anymore. So if you think about computing this matrix product here just in the normal algebra, so for example, for this data point, you multiply here the 1 times the 1. So this is 1 plus this 1 times 1. So in this overlapping area here, you get a value of 2 in the normal algebra, which then again introduces an optimization, an approximation error, right? Because you have a binary data matrix. So in Boolean algebra, this overlapping area will also be reflected as a 1. So it does not penalize overlap anymore. So what can we do now if we cannot apply the alter minimization of k-means? We do basically what we did also for NMF. So we use now alternating linearized minimization. And you might remember that for this alternating linearized minimization scheme, you need the prox operator. Now, in this case, I have just proven the prox operator, so the analytic solution for the proximal mapping for this penalization function. So basically, it returns infinity if we're outside of the interval from 0 to 1. So we will stay inside the interval from 0 to 1. And you see that just 0.5 is penalized the highest. And then it's basically a linear relationship. So 1 and 0, the binary values, are the only ones which are not penalized at all. And if you then show or derive the optimum of the proximal operator, which gives always a nudge into the direction which minimizes my penalization term, then you arrive at the proximal mapping, which basically pushes any value which is on the right of 0.5 further to 1, and every value on the left of 0.5 further to 0. Now this looks then as follows. So we have this objective here, and phi is this penalization term with the roof basically. And yeah, so the process that we have now is theoretically founded numerical optimization. And we do not need anymore this exclusivity assumption. So Y is now any binary matrix. It doesn't have to be this partitioning matrix. And in the end, so depending on the regularization rate of this function here, you get matrices which are at least quite close to binary matrices, or which are actually binary. So, but because sometimes you maybe don't want to optimize all to the end, because it might also take a bit longer, you want to just get the general gist of it. So what are the approximately binary matrices? And then I just threshold, so I discretize. But the thing is that if I discretize, then a bit of theory gets lost, right? Because here I know that I have that I converge to a local minimum, but if I discretize, my theoretical guarantees get lost. And also, generally, this is known that the scaling of matrices during the optimization, if you use a penalization term like this, is an issue. So there just have to be always found some workarounds on that. And as a result, I wanted to show you this. So here we input an image, and the task is to find a Boolean factorization, which basically clusters the elements in the image. So this image is represented as a binary data matrix by basically taking here rectangles of cutouts, basically. And then every pixel is reflected in its binary values of the RGB format. So in this value, you have like a pixel represented as 1, 1, 1, 1, 1. So if you have all ones, then this represents the color white, and everything which is like a combination of 0 and 1s is then introducing some color. And when you now cluster with Boolean matrix factorization this image, then you see that the heuristics which so far have been applied actually, always overshoot a bit. So for example, here in this method, the first outer product, so the first bicluster, is already representing all the shape information. But because we have here white, and white is 1, 1, 1, 1, 1, we cannot repair it afterwards, because everything we can do in Boolean algebra is add something, right? We don't have a -1. So in the end, you get here this paper, which is a black and white representation of your space invaders, but this doesn't really give you a good clustering. Now this here is actually quite nice, but you also see that it's not very exact. And now if you do it then with the proximal alternating linearized minimization, then you get these two results. So here we have a rank of 2. And then in this rank of 2, basically it interprets all deviations of the color pink to blue as noise, and all of the deviations from the color turquoise or cyan to 0 also as noise. So it just distracts the yellow and the blue channel. And if you have a rank of 3, then you can see that actually it derives the suitable clustering. Maybe not the one that you would expect if you look at it as a human, but it's a totally valid clustering to separate it by the color channels. No, the research directions here would be that, first of all, many of the one-sided clustering tricks are taken over for biclustering, but having two binary factor mazes poses additional challenges. So this is just a thing to work with. So actually biclustering is a bit more difficult to optimize. And penalized matrix factorization is also, again, strongly related to penalized regression. So if you're an expert in penalized regression or like in regression solutions, it might be interesting to try this also if it works for clustering and vice versa. And biclustering optimization is also relevant for tensor factorization. So for example, if you want to have a task like knowledge base completion, so usually there you have a knowledge base which represents, for example, Paris is capital of France. And then you have in the tensor for Paris and is capital, and France you have a 1. And then they use actually matrix factorizations for completing this knowledge base. But the matrix factorizations, they are just like the standard ways, like SVD type factorizations. So having here binary constraints could help in the interpretability of what you actually get. And another interesting research direction is, I think, to use autoencoders for pattern mining. Again, this shows a bit the relationship of like deep learning methods and clustering, and how, for example, also the binary, the binary tasks like pattern mining are translated here. Okay. Any questions so far? Then we do something different now. Deep learning. So, okay, I'm maybe a bit like a crazy person, but I see k-means everywhere. And so I see k-means also in deep neural network classifiers. So in fact, what I've shown is when you have a neural network classifier. So basically you have here your input, and then you have your layers, nonlinear activation functions, and so on, until you arrive here at the penultimate layer. So this is the layer before the last layer. So what you do basically then to classify, you have here your feature transformation into the penultimate layer. Then what you apply is your last multiplication with the weights, and then you apply softmax, and then you get the probabilities and confidences for your classification model. Now, in this space here, this classification, for this classification, you can also find centroids which actually induce the classes. So for every neural network, you can find some centroids in the penultimate layer space such that you're actually doing a nearest centroid classifier. So this is basically what k-means does when it assigns its points to clusters, right? You take the nearest centroid, and this is then the cluster. In this case, it's then the class. Okay, why is this relevant? Well, one of the things is that the penultimate layer space shows that it separates into softmax assigned classes super confidently. So here you see, for example, the class boundary. So this is, for example, for class 1. This is class 2, and this is class 3. Now you have like a finite training set, right? So the number or the amount of all the points which are assigned to class 2 will be here in some kind of bounded region within the space of class 2, right? And if you now take a sample on which you didn't train before, or which is out of distribution, and it lands like far outside here, then it will be very confidently still assigned to class 2. Like the further you go away, the higher your confidence basically gets, if you do not by chance land exactly on the decision boundary, which is just, not so likely. So why is this a problem? Now, there was this image which I liked a lot, that softmax confidence, showing that softmax confidence is just often overconfident. So people have trained a network to identify COVID-19 in a picture of the lung. And then you see, you put in a picture of the lung, it says like it doesn't have COVID or it does have COVID. And if you insert the picture of a cat, it says like with near 100% confidence, the cat has COVID? I don't know. So maybe, but that's definitely not what it's supposed to do, right? So this is a problem, and softmax has no possibility to reflect what it doesn't know. This is a bit of an issue. So using another confidence would make sense. And if we now have already this relationship of nearest centroid classification, why would we not use this for a confidence? So what we propose is here, for example, an RBF kernel-like confidence measure. So only those values which land in the penultimate layer space here close to one of the centroids are confidently assigned to the corresponding class, and everything which is outside is just not confidently assigned to any class, so it's supposed to be an outlier. And a centroid-based confidence makes deep neural networks also more robust to attacks. So the issue with adversarial samples is, for example, denoted here. So you train, for example, on ImageNet, and then you give it the picture of this panda, and it says it is a panda with 60% confidence. Then you add super small amount of noise. So this is here your noise picture, and epsilon is super small. It's so small that actually if you add the noise to the image, you cannot see it with the human eye. So you cannot see the adversarial disturbation, and now the network classifies the panda as a gibbon, so as a monkey with a super high confidence. And this you can do also like with other classes. So for example, it's also easy to make it say it's a bus, you know. So this is a problem for the trustworthiness of deep neural networks. But actually, if you use centroid-based confidence, then you can derive a guarantee on the minimum amount of the perturbations that you need in order to make an attack, an adversarial attack, successful. So for example, X is here in the feature space, so it's an image like the panda, and X plus delta is the adversarial panda. And then if I map this to my penultimate layer space, and if phi from X would actually be confidently assigned to a class, I know it's close to my centroid. And now to push it actually to the other centroid, of course, like the minimum amount of disturbation I need depends on the distance between these two centroids. And it depends on the distance between the two centroids. So basically the margin, which could be interpreted as a margin between the classes, and also the Lipschitz constant of the network. Now, the Lipschitz constant is generally this obscure thing which is always needed for more robust deep learning. It's just super hard to control, to compute. It's a pain in the ass. But at least it gives you some kind of idea about what's happening. So centroids further apart is better. Actually, if you don't know, so the Lipschitz constant basically bounds how much something which is close in the input space can then be pulled apart in the output space. So if the Lipschitz constant is 1, then this distance here is at least maintained, right? So then phi from X plus delta can be at most as far away as X is from X plus delta. So the smaller the Lipschitz constant, the more local similarities are actually preserved. And now I wanted to show you, Naya, just an example of like, if I train, for example, on MNIST, just on 5 classes a neural network where I have in the penultimate layer space a dimensionality of 2. So then I can really look into it and see what's actually happening. So this is not a projection. This is really what the network learns and how it classifies. And here you see the classes. So here the class 0 has just a very small area actually. And here you have the class of 4s, here you have the class of 3s, of 2s, and of 1s. And you see that most of them are aligned on this middle axis, basically, which represents the softmax confidence thing, which is represented also by the inner product. So basically, here you have like most confidently an assignment to the classes, but you also see that the confidence generally is very high if you're not on the boundary exactly. And now if you use here Gaussian deep neural networks, so with this Gauss confidence, then you see also more what are the prototypes of my method, right? So those which are, for example, the ones which are very confidently assigned to the class of ones are actually quite straight. And those ones which are a bit more, in a cursive style, like left or right, they are actually pushed a bit more to the boundary. So you see that the network actually considers this as outliers. Likewise, this thing here, I hope you can see this, but it looks a bit like a 1, but it could also be a 2 because it has a small thing at the end. Now this thing is also between 1 and 2 here, but it would be still confidently assigned to a 1. And here you find this image here. So it's basically between the cluster for the 2 and the 1. So you see that there is some semantic information. And I think this illustrates, a bit like what could be nice here, because, for example, if we would also find this non-negative constraint again, such that you build together your images. So, for example, the 2 can be represented as a 1 and a thingy at the end, right? Or like the 4 is basically a 1 plus another sign. So this could give you more of an idea about what your network learns. So I conclude with the research direction. So can we use, for example, also multiple centroids to provide interpretable deep neural networks? So maybe you need one centroid for the ones which are very straight, and one centroid for the ones which are like this, and one centroid for the ones which are like this. And in each case, you can say, like, what is the prototype of my centroid, which again gives you a bit of an idea of what the network confidently assigns to a class. Then this bridge between k-means and deep neural networks is also quite interesting to actually explore the clustering properties of deep learning classifiers. So there are some first approaches here. And the last thing is, can we create a kernel by clustering extension of deep neural networks, identifying, for example, areas in a picture which determine the class? So, for example, in ImageNet, you have often these images of a guy with a bow tie and a fish in the hand. So then the correct class is fish. But sometimes if you evaluate the robustness to a text, then you see that some of the attacks say, oh, it's bow tie. I mean, the network is then not wrong, right? But what I would like to have is actually an inbuilt identification. For example, with binary values, identified with binary values in my network, which identifies exactly the pixels that are relevant for my classification output, such that I know, okay, if the output is bow tie, what did it look at? Oh, this thing. I mean, there are these saliency maps and so on, but they just don't really capture what the network is actually doing. They just, like, fit something which is nice and neat, but not necessarily true, as Katharina already said. Okay, that was it. If you're interested, you can contact me. My email is here. I have given also a tutorial on this topic. You can check out this website here for it. And if you want to see on my website, I also have some teaching material which goes a bit more slower to some of these concepts. And I just assume that the slides will be released also, right? Okay, thank you.
Yeah, so any questions? Yeah.
The Gaussian confidence that you proposed, is it something that is already solved, or would it be something that's nice to have? Can you approach it with a different loss function, for example?
Yeah, so we need a different loss function because cross entropy always has this idea that you have the probability vector. But here we also want to allow for outliers. So we also want to have low probabilities for all classes, and then this wouldn't work with cross entropy. So workaround is to use a binary cross entropy loss. It has some trivial solutions which are not desirable. So you have to work around the optimization becomes a bit more complicated. But so our solution is to actually train the network with like 30 epochs or so, have a warm start. So we train the network such that it gives an outline about the classes. And then we compute the centroids according to the result that we can actually compute the centroids. And then we fine tune based on this initialization, the confidence measure.
Okay.
And this works quite okay. We're working on it.
And do you think you could combine the two types of confidences? Because this geometric Gaussian-based confidence seems to me like something that has to do with stuff that happens outside of your data set. And maybe for the inside of your data set, you want to have these probabilistic interpretations that might be overly confident, but only to the degree that is inside your data.
So do you mean that you overlay the confidences, or that you basically have different outputs giving you different confidences, so based on what you want to see?
Like a fallback that tells you, I am confident that it is this class, but only given this confidence that it is within the data that I've seen.
Yeah, that could be interesting. But I think maybe then it would be also, you maybe could do also just a post hoc step, right? Just cluster in the penultimate layer.
Yeah.
For example, with also like dbScan or whatever, and then basically get an idea where are the data points usually landing in my training data set. And if it's just outside, then I just don't confidently assign. I think this could be an elegant option if you, for example, don't want to change the training too much. You know, if you already have, for example, network given and you just want to have some insights into it or results about it, or to make it more robust, the network that you have given. People have done this, for example, for Bayesian networks. I know that it works okay-ish, but it's not super tight as so far. So they also learned Gaussians, but then actually also multivariate Gaussians. So they could also model ellipses and so on. But it's not super tightly somehow adapting to the training data. So it's still a bit doing some things which it shouldn't do. But it's relatively new, I think, this line of research.
Okay, thank you.
Thank you.
So any other questions? Yeah.
Thank you. So my question is related to the centroid-based Gaussian confidence. So my question is, does this then learn to overcome only one specific kind of noise, or is that generalizable to any possible kind of noise? So the thing that I'm asking then is whether that is learning actually the noise and how that could alter the data, and if this approach is generalizable or not.
So yeah, I mean, in the end, what it's learning is basically what is the area where my training data usually lies.
Yeah, so just to rephrase my question is, so I know that the problem is that you are misclassifying something. And so you want to make the two elements to be far apart. So actually they fall into different clusters. But the thing is that maybe depending on the kind of a noise, on the noise distribution, then, so for some noise, then this approach, so that is just some, I'm thinking out loud. So maybe for some noise with a given distribution that works, but with other noise, with different distribution, I'm just guessing, it might not work. So my question is, then is this kind of approach learning a certain kind of noise distribution, or is that actually generalizable to any kind of noise that could be inputted into the data?
So from my experiments, I would say it's generalizable. So what we did to evaluate this is just to see how well different attacks work, because various attacks like have different approaches to generate the noise, and they always want to generate the noise such that it actually fits your model, right? Such that basically it exploits weaknesses in your model. And usually the attacks are notably less successful on these networks. So I would say that it's not very specific to a particular kind of noise. But of course, it's not like entirely solving the problem, right? Because for solving it, we really would have to also control the Lipschitz constant, which just nobody knows how to do this at the moment. It's super impactful area of research, I think, but yeah, we're still at the beginning there. And also, I think sometimes it's a bit of a question. So what I tried is to just like, okay, I can't do anything about the Lipschitz constant, so maybe it goes up, whatever. But I want to tear the centroids apart. But also that is not so easy during optimization. So at some point it just breaks. It can't do any further. So this is the question, like what happens at this point, you know, like is this like a maximum Lipschitz constant also that is reached there or something like that? So this should be, yeah, it's all interesting to research.
Okay, thank you very much.
So we still have time for one more question. So do we have any question online? No. Okay, so thank you for your talk.
Thank you.
Yeah.